We are continuing on with class number 15 with yet another example. Here's one on a Borgnagi. It's problem 471. We have a mixing chamber that receives refrigerant 410A, 2 kilograms per second of it, at 1 megapascal, or 1,000 kilopascals, that is, 40 degrees Celsius, and that's in one line. In the other line, it gets 1 kilogram per second of the same refrigerant. Don't want to mix refrigerants, but this time at 15 degrees Celsius with a quality of 50%, in line with the valve there. The outgoing flow is 1 megapascal. So I would think that they're all 1 megapascal or thereabouts. It would make sense, but, or I guess it would need to be at least, I mean, yeah, the mixing one needs to probably be maybe more. I don't know. Needs to overcome that. They need to mix together, that's for sure. The outflow is 1 megapascal, 60 degrees Celsius. Find the rate of heat transfer in the mixing chamber. In the mixing chamber. That's interesting. Okay. Well, oh, okay, I see what they're saying. But what they're saying, and I didn't understand this the first time, and of course I'm rereading it again, and I didn't understand it the first time. They didn't really quite make it clear that there's heat coming into this, right? So this is what we want to try to find. I was thinking of the heat transfer inside this thing, but this is the amount of heat transfer that must be placed into this thing for this thing to be possible. So that's an important thing. We would need to get some qualities, or get some quantities, especially enthalpies for all of this stuff here. So let's start out by going to table B.4.2 and get the superheated one. So if we get at the pressure, we'll call it 1 because it is, for that 1,000 kilopascals, and a temperature of 40 degrees Celsius. We find that H1 is 316.05 kilojoules per kilogram. And then we'll go and get this guy, I guess. So we have to go to table B.4.1 for that. And I got to go to a T2 is equal to 15 degrees Celsius. The PSAT, if we wanted to know that, is 1,255. So it has to be larger to be able to squeeze back into the thing. Problem is it could force that to go back out, right? No. But anyway, they said there's a valve there that allows it somehow to get in. Magical. The HF for this is 81.15 kilojoules per kilogram. HFG is 201.64 kilojoules per kilogram. So we get an H2 equal to HF plus X HFG, or 81.15 plus 0.5. They said it was 50% up here, so we're going to do what they say. And 201.64. So we're going to get an H2 of 181.97 kilojoules per kilogram. And lastly, okay, we're going to go back to table. Probably could have stayed over there. Table B.4.2, and then at P1 equals 1,000 kilopascals and 60 degrees. T3, I didn't mean T1, T3, is equal to 60 degrees Celsius, which is surprising because it's larger than these others. But then it was like, oh yeah, there's heat being added to it. Really bothered me when I first did something. Like, how is that possible? I can't make it. Like, oh yeah, no, they're adding heat. They didn't say how they did it. It says 335.75 kilojoules per kilogram. So conservation of mass. M.3 is going to be M.1 plus M.2. And they made this kind of easy for us because you had 2 plus 1. I could do it. I'll use the parentheses when I get an answer. 3. I'll give some sig figs just because I'm making fun of myself. Then we go to conservation of energy. Boom. And I'll write out the equation. Q dot minus work dot, aka power, plus summation of MI/HI minus summation of MEHE. Forgot to put dot. No work. We have our Q, and then in M.1 H1 plus M.2 H2 minus M.3 H3, which we could also say was equal to 0. There's the thing that we want, plus 2 times H1, which was 316, plus 2 M.2 H2, which was 181.97, minus M.3, which is 3, H3, which we just found here, 335.75. We get a Q dot of 193.2 kilowatts has to be added to this in order for this outcome to take place. So it wasn't just a mixer, it was a mixer heater. All right, so we'll do 2 more. Wow, what's wrong with me? Yeah, 2 more. The next ones are going to be Sengel examples. Another mixer and a cooler, another heat exchanger. Have a great day.